Yeah. Hi everyone. So today we have Apratim Kaviraj from DESY. So okay, over to you, Apratim.
Thanks, Subbu, and it's a pleasure to be here to give a talk at. Okay, so it's a big name, low energy. Okay, LETHEP. Sorry, couldn't remember the whole thing.
Yeah, it's
so, fine. So my talk is on analytic functionals and global symmetries. So it's based on an upcoming work that I'm doing with Kaushik and Miguel Paulus. So it's a so I'll try to be as informal as possible. So you should always stop me to ask. But it can be a bit technical, the talk. So whenever you feel uncomfortable with something, with notations or with anything, so please stop me and ask questions. And since it's so let me show you the outline. So the first part of my talk will be based on some basic things like analytic functionals introduction and some basics of Bootstrap. So this part itself is quite technical. But it's also mandatory because I have to give this introduction in order to show you what comes next. So please feel free to stop me anytime that when you have a question. So after with an introduction of this analytic functionals in 1D, I will move on to the global symmetry functionals, which will be the main topic of the talk, and I'll show you two types of these functionals that we have worked on, and also their connection to Polyakov Bootstrap and how to derive some bounds with these functionals. So as I told you, this will be a generic global symmetry functionals. I mean, this will be based on a general global symmetry, but I will, for simplification, I will mostly work with the ON models just to make matters simple. And if time permits, I will show some applications of this whole thing. So as I told you, I am working on this with Kaushik, and he's also there in audience. So if I say something wrong, Kaushik, please correct me. Okay, so some basics of Bootstrap and global symmetries. I'm sure that many of you have heard, I've seen these things in a lot of other talks, but still it's a mandatory introduction. So I will start with a simple 2-point scalar OPE. Scalar OPE, two scalars whose upper product expansion has the following form. And you can use this 2-point OPE in any general endpoint function, especially here I have written out a 4-point function of scalars. And what you can do is you can use this OPE to expand two scalars, the first and second, or the third and fourth. And this way you get an S-channel expansion where this guy is the conformal block, this G is a conformal block, which is basically like a product of these guys, fx delta, fx delta. And then you can also expand this thing in the T-channel block, which is like expanding the first and fourth and second and third operators, which gives you the T-channel, which is also a conformal block, but its arguments are given by 1 minus z. So the T-channel, S-channel and T-channel are related by changing z to 1 minus z. While z is a cross ratio, it's given by the following. It's given by there's differences of the points where xij is defined as follows. So the bootstrap equation is basically equating S channel equal to T channel, which can be simply denoted by the following expression, bootstrap. And well, where this f minus is called a bootstrap vector. It's a combination. It's the difference of the S channel and T channel conformal blocks. So yeah, this is the very most obvious things. So the same, you can do the same thing for a model with global symmetry, where so for global symmetries, what you do is you take the OP of two scalars with global charges I and j, and the operator that gets exchanged in the OPE they also carry two charges I and j, and it can be, and this operator can be singlet or crystal symmetric or an antisymmetric operator. So here I'm working with the ON models. So this is just, as I told you, it's just for simplicity, and you can take any global symmetry you want, and working is very similar. So now what you can do is you can use this 2-point OPE in a 4-point function, and then it gives an expansion as follows. So here you have the singlet channel, the singlet sector, and then you have the traceless symmetric and antisymmetric. So this is how it breaks down the 4-point function of 4 scalars in a global symmetry. So this is the S channel expansion. This whole thing was an S channel expansion, and you can similarly have the T channel expansion as well, where the T channel is obtained just by swapping Z to 1 minus Z, and also changing the when indices from I going to K. That is, you really have to change the fields, swap two fields around to get the T channel. So how do you obtain the bootstrap equations from this? You can just recombine recombine the S channel and T channel, and then recombine, and also you have to contract with the invariant tensors, which are like delta ij, delta kl, or the traceless symmetric combination delta ij, delta k, delta ik, delta jl plus delta il, delta jk minus blah blah blah. So you have to contract with these invariant tensors, and this would give you the ON bootstrap equations. So there are 3 of them, because there are 3 sectors, and yeah. So and the first of these two equations, these two equations involve F minuses, and the third equation involves F plus, and F plus is given by plus combination, a symmetric combination of S channel and T channel block. So this is the beginning of, so this is the basics of the bootstrap and its extension to global symmetries. So any questions so far?
Pratim, can you go to the previous slide? I just want to look at it once.
Which one? This one or the?
No, the slide before.
Yes.
I see. So the first step I understand, you are just decomposing it into reps, the
Right.
OIJ,
Yes.
right? So
Yeah.
in the second step, I see you're saying, for example, that I and J, when they fuse into the irreps again, right? That's
Yeah, yeah, yeah.
I
Yeah,
see.
exactly. It's just like the without
Yeah.
global symmetry case, but it's the same thing, but you just get singlet or
Right.
symmetry and symmetry, different tensor structures. But
Okay.
it's similar to, yeah.
Okay. Okay. Great. Okay. Yeah. Go ahead. Yeah.
Okay, so if there are no other questions, I will move on to the introducing to you the analytic functionals in 1D without global symmetry. So this is without any global symmetry. Okay, so let me begin by saying that if you have a bootstrap equation in in uh, um, in 1D and without any global symmetry, it is basically solved by using a set of functionals. So a functional is, well, so if you have some functional, for example, a functional can be a basis of derivatives, like derivatives of z. By the way, if I haven't mentioned it already, so yeah, so for 1D you just have one cross ratio. So also this derivatives will have just one derivative, del z, with z at some certain point, for example, z equal to half. And you can use this basis of derivatives to expand the bootstrap vectors, or it can be any functional you want, but these functionals they have to act on the bootstrap vectors and give you some equations which you have to solve for like the following. So if you have a functional, in general, I will just denote a generic functional as an omega. So this is like my notation for a generic functional. And I will also use the notation omega of delta, by which I will simply mean the action of a functional on f of delta. So when the functional omega acts on bootstrap vector f minus, it gives you a number which gives you a function of delta, and this I will denote just simply by omega delta. So please remember this, because this will appear several times in the talk.
Can you once again show the bootstrap equation?
Sure. It's this. It's the following.
Yeah. So by solving, what exactly do you want to solve here? Like find expressions for f delta.
Right. Well, f delta is something that you already know, and by solving bootstrap equation, I mean solving the OP coefficients and the dimensions, conformal dimensions. So this is like the simplest way of saying it.
Okay, so C delta, those are given.
No,
right?
nothing is given. So, I mean, it's the only thing that you know is the expression for the conformal blocks, and when you solve a CFT, right? So thanks for asking this. So I should make it clear that when you solve a CFT, you just know the expression for the conformal blocks, and you know that it satisfies crossing.
Okay.
And you can have some extra conditions, like it's unitary, the theory may be unitary, has unitarity, and unitarity would imply positivity of OP coefficients, but you know nothing else. So the C delta and deltas are all unknown, and you have to solve the bootstrap equation in order to constrain the OP coefficient C delta and conformal dimensions delta.
Okay, thanks.
Okay. So, and for the use for the analytic functional is that the functionals basically act on the kinematic equations f of z to give some equations that you can actually work with, some algebraic equations or something like that, so that it's possible to solve them and get some actual constraints or solutions. Oh, all right. So if you have a functional, it is also necessary for it to have certain properties. And one of the most important properties that are usually desired is the property of positivity. And so by positivity, I mean the following. That's, for example, let's say that you have a functional with the following positivity properties, that it has its action on the identity is the following. So by the way, so identity is given by conformal dimension of 0. So its action on the identity. So if you have a functional whose action on the identity is greater than or equal to 0, and its action on any other generic dimension is also positive, non-negative, if delta is bigger than a certain value, delta G. So if you have these properties, you get bounds from the operator spectrum, right? Because in order to solve the Bootstrap equation, you cannot have all dimensions which give a positive value of the functional, because in the end they have to add up to 0. So you need to have something for which omega should also be negative. So it's simple. So if you have this kind of positivity properties, it automatically implies bounds on the operator spectrum. For instance, here it will imply a bound on, for instance, this will imply a bound on delta G, but delta G is like the minimum, the operator with the minimum conformal dimension above the identity, the first non-zero non-identity operator. So it implies a bound on that. So now let's say that you have a bound, and then and you happen to know a CFT solution, that saturates that bound. So suppose this happens. If this happens, then you call this an optimal bound. So we call this an optimal bound if you know a CFT that is saturated by saturates the bound. So by that I mean that, for example, suppose you have a delta G less than equal to something, and you know a CFT that has delta G equal to this guy, so it saturates the bound. That's what I mean by saturation. And what will that imply on the functional values? It will also imply that, so say that the CFT is given by the following, that its identity, it has the first operator which is delta G, and all the other operators, if they're there, they must satisfy that the action of the functionals on them, they're identically 0. So if this saturates, this is an obvious property to have. So this solution I would call an optimal solution, and it was shown in the following paper that if you have such an optimal solution, you can systematically build a functional or some functionals that trivializes their solution, just like the following, just like what you have above. So for any optimal solution, this can be done. So you can build a set of functionals that makes that trivializes that solution, that CFT.
Pratim?
Sure, yeah.
So are you going to discuss like how is this handled? Like, do you do it analytically? Like how do you find a specific functional?
I will, yeah, of course I will describe this, but I will describe this not for a generic solution. I'll describe it for one particular solution, which is
I
what
see.
I present next.
Okay. Okay, great. Okay.
So yeah, so right. So as I so as I just said, that I will focus on one particular analytic solution, which is the generalized free fields, and its form is very well known. It's basically the following. So it's given by this code letter. This is the code letter of a generalized free field. This is how it's defined, and it's well, it's, you can see it's already, it's crossing symmetry, and its dimensions are given by the following. It's given by the identity and double field operators. So this is a quite well understood, analytically well understood solution, and what I call analytic functional is a set of functionals that optimizes this solution, generalized free fields. That's the definition of analytic functionals. That's what analytic functionals are. And before I move on to how to describe, how to define them, how to build them, I just let me advertise them a little bit. So that some advantages of having an analytic functional over usual derivatives is the following: that it already gives you, gives you some nice analytic understanding of bounds and solutions. By this I mean that suppose you want to solve for a CFT which is perturbatively away from the generalized free fields. It's very easy to do this with analytic functionals. Also, if you want to go after some numerical bounds, it's the same story, that you have on your back of your mind an analytic picture to work with. And for the examples I'll show this, I hope this will be clear what I mean by this. Also, it's the analytic functionals are always way faster. They have a faster convergence property, and this is evident because usually they are built to optimize generalized free fields, and this solution with the derivative functionals, it takes an infinite number of derivative functionals to get to the GFF solution. So as I show you here, so it's a simple way of showing this. It's that suppose you want a solution which has the following, which is like perturbatively away from generalized free fields, or well, yeah, like the following. You can have g small or 0, g small or even 0, whatever you want, and you can, and if you try to maximize the OP coefficient of the first operator, so this is called OP maximization problem. So suppose you have this assumption and you want to maximize the OPE of the first guy, delta 0. Then, well, with the basis of derivatives, you can keep using many derivatives, which is this, the number of derivatives, and you can see that, well, the number of, you keep getting many operators in the theory, but they are never they converge to the right answer, but they are never really there. So this convergence is really slow. But with the analytic functionals, it's just the green lines. So these green lines are the analytic functionals. They'll almost immediately give you the right answer. So, all right. So now let me show you how to build the analytic functions. Okay, so to get there, let me so first let me introduce to you a basis for expanding the bootstrap vectors. So a basis, so I claim that there exists a basis for the bootstrap vectors as the following: that any bootstrap vector f minus, which I explained, which, let me remind you, it's like g delta z minus g delta of 1 minus z. So it can be expanded in a basis of f minus of double trace guys, double field operator guys. So, and I denote them as delta n. So by the way, this is another notation that I just introduced. So there will be many notations. So please stop me if you're confused about something. So in this basis, so why does this basis exist? So this basis exists. Yeah.
Sorry, I'm unfamiliar with this. So so two questions. So what are double fields, and are these f minus delta n known?
Right. Yeah. So f minus delta. So what are the double field operators? Double field operators are schematically, you can imagine them to be operators like the following, like n derivatives.
Another field. I see.
Yeah. Essentially 2n, and then another field.
Okay.
Well, and this f minus is defined by the following. So it's just this 1 minus this. They are the anti-crossing symmetric combination of conformal blocks.
Okay. Great. Okay.
All right. So yeah. So why should this basis exist? So the existence of this can be easily seen by considering a combination of exchange Witten diagrams like the following. So exchange ADS2 Witten diagrams. So an ADS2 Witten diagram, so you see that this is a manifestly crossing symmetric thing, and it can be easily shown that it has a conformal block expansion like the following. So it has a conformal block expansion, and since it's crossing symmetric, it also must satisfy the bootstrap. Satisfy the bootstrap equation like f of delta equal to 0, right? Because it's crossing symmetric and it has a conformal block expansion like this. And what I have written above, so what I've written above here is basically the bootstrap equation for this crossing symmetric quantity. So this GFF basis that I wrote down is nothing but the bootstrap equation given for this crossing symmetric combination of exchange Witten diagrams. So it shows you basically that f delta z can be expanded in blocks of double trace operators. So now, so if this basis exists, it should be possible to have a functional that gives you these coefficients. So it should be possible to, it's like Fourier transform. So you have a basis and you should have something that gives you the precise coefficients. So the analytic functionals are nothing but what gives you these coefficients. So these analytic functionals there are two types, so omega equal to alpha n or beta n, and they're defined as follows. They're defined by an integral of dz and a certain functional kernel f, and another integral over the following, over this region, and another functional kernel g. These are functional kernels, and they're also related as for, so f and g have some relations between them, and they are given by the following. So f and g they're related in a certain way. And the action of a functional, so omega delta is basically nothing but if these integrals acting on the conformal blocks like the following. So this is how they are. So this is like the definition of the integral, and you also have to constrain f's and g's such that they give you the basis vector coefficients. And this is ensured by demanding the further conditions of orthogonality that says that a functional alpha acting on a functional alpha n, there are like the functional alpha also has an index n. If it acts on a bootstrap vector of double trace guy delta m, then it gives a Kronecker delta mn. And similarly, the betas, the derivatives give at the same position give a Kronecker delta m. The derivatives of alpha gives a 0 and derivatives of beta gives a 0 at the double trace operators. So this, if you look at this coefficient, these relations properly, you can immediately see that if these are true, then they will automatically give these coefficients. These alphas and betas will just pick out these coefficients for the double trace guys. So this is what the orthogonality conditions mean. There are some further conditions that should also demand that their action on the block should be finite. This is obvious because their action should be finite. And also they should respect swapping, which means that any functional which acts on a sum over a full correlator, which is a sum of blocks, an infinite number of blocks is just given by an infinite number of the functionals, the action of the functionals. So it looks like an obvious relation, but well, it's not so obvious if you have an infinite number of guys to sum. And this is ensured by a property called Regi boundedness property, which the Regi boundedness is, so it basically comes from the fact that a full correlator is always Regi bounded in this limit, and in this limit, so it satisfies. So the kernels must be such that its action on the individual blocks and the full correlator, they're both finite. So, and this is by looking at the Regi boundedness condition of the correlator, this is ensured. So, is there any questions in this part?
Can you go back to like 2 slides before where you gave this expansion?
Sure. Yeah.
Okay, so this was the expansion in terms of this basis. So
Yes.
So now the aim is to determine alpha n and beta n, is it?
Right. Yeah. And this is exactly.
I see. So now in the next slide, you are defining this omega
Yes.
with given f delta z. Is that?
Well, yeah. So I know the big F's, I know, and right. I constructed omega by choosing some smartly chosen F's and F and G's, small f and small g, such that they pick out the coefficients. It's as
okay.
And getting them is a bit non-trivial, so I have skipped all the details, many of the details, but essentially it's
I see. Okay.
Right. Okay. So okay. So now that you know the functionals, I will tell you about a bit about their connection to the story of Polyakov Bootstrap. So the story of Polyakov Bootstrap was well, you can see, you may have seen them. There, many people have worked on that. So, so in short, the story is as follows: that one claims that if you have a 4-point function, if you have a 4-point function, it allows an expansion in Witten diagrams. So these are exchange Witten diagrams. Exchange Witten diagrams in different channels, and a certain contact diagram. And the idea of this expansion, why does it matter to have this expansion, is that this whole thing is a manifestly crossing symmetric thing. Manifestly crossing symmetric. So one claims that this is possible, but if that is possible, then it should also be equal to the usual OPE. Now, if this is true, then this gives you the first line of this is basically the usual OPE, the usual OPE. And the second and third lines are basically the some extra guys, some spurious blocks, which comes from the Witten diagrams, and they must be set to 0. So these guys must be set to 0. So this is the idea of Polyakov Bootstrap. So I'm being super short, but so this in high dimension, it showed that it gives some really nice results, although there was not really a very rigorous proof. So it was there wasn't a rigorous proof before. Now there is, and so it was still pretty well established. And so
Apratim, one question.
yeah.
Is there a physical understanding why the T and U channels give rise to spurious poles? If I understand correctly, so in your slide, you're showing that the spurious poles, do they come from the exchange Witten diagrams from T and U channels specifically, or from S also?
Also from S. So from all of these things, it's basically, so let me, okay, I haven't written, so let me write down. So okay, here let me write down the expression for the Witten diagram. So Witten diagram is in the S channel Witten diagram is given by the following. Is given by, so an extent by the way, an extent Witten diagram is something like the following. It's exchanging an operator delta, and this is given by a conformal block of dimension delta and the sum over an infinite number of double trace guys like the following: 2 delta phi plus 2n plus derivatives of 2 delta phi plus 2n. And this, what the T channel guy is basically, the T channel guy, if you expand, so this, the first line was an expansion in crossing symmetry in S channel conformal blocks. The T channel Witten diagram is, if you expand them in S channel conformal blocks, so this is important that you have to expand them in S channel conformal blocks, then you get something like ANT G of delta n again, and also ANT of G of delta n plus 1s. So there are, so you get both. So previously you had 2 delta phi plus 2n's, and here you have 2 delta phi plus 2n plus 1s and their derivatives. And so this is the expansion. So you get spurious poles from both of these things, but there's an extra spurious poles in the T channel.
So is it right to say that spurious poles are coming from the additional terms? Meaning, what I'm confused is this G delta of Z. Does
Yes.
that also contribute to the C delta plus spurious poles? Or
No. Right. Thanks for pointing this out. No. So it's just, so this D delta directly comes here, and everything else that I wrote down here, they are, you have to collect them and order by order set them to 0.
I see. Okay. Thanks.
Right. Thanks. Okay. So that was Polyakov Bootstrap. And the connection to the Polyakov Bootstrap and the functional Bootstrap equations, by the way, if I haven't made it clear already, the functional Bootstrap equation is like sum over alpha. Well, it's basically this. So I already have it here. So they're both given by the same thing. So you see that the functional Bootstrap equations are just the functionals alphas and betas acting on, so the alphas or betas acting on the Bootstrap vectors C delta equal to 0, and it gives you these equations, and so does Polyakov Bootstrap. So the only so they are equal if you choose the right basis of exchange and contact between diagrams. So this is the whole thing. All right. So I move on to a simple demonstration of what these alphas and betas are, and so how they look like. So they look like the following. So the alphas and betas, if you plot them, if you plot their values of their dependence on delta with delta, they look like the following. So these alphas basically have their zeros at all these positions because they trivialize general registry field. So they are zeros at all the double trace values, but alpha n is non-zero, is at when the dimension is delta n. Similarly, betas are also zeros at double trace values, but it has a single, but all these other positions it has double zeros except here where it's a single zero. So this is the respective properties of alphas and betas that allows them to get something useful. And very similar, and well, so this is like the last slide of my introduction. And here I point out that quite similar to the minus type function, that just like you can have crossing symmetry, you can also have anti-crossing symmetric equations where you can have these involve f plus z's, where f plus z is defined by a positive combination of conformal blocks, and also for these guys you can have functionals. They are called plus type functionals. So the plus type functionals, the method of getting them is very similar to alphas and betas. So I don't mention them separately, and the properties are also similar. So everything for whatever I just told you about minus type functionals, they can be done for plus type, with alpha plus and beta plus chosen in a proper way. So any questions so far? I'm going to move on to end. So yeah. All right, so I move on to ON models. So global symmetry. So for ON models, for example, as I showed you before, they have the following bootstrap equations. So there are 3 of them, and they can be, so f minus and f plus are given by the following, and they can be written in a compact way. So the 3 bootstrap equations can be written in a compact way as follows. They can be just written as a system of matrix equations, where these guys, these vectors, these are called ON vectors. So there are 3 of them. One for the, so let me remind you that one for the singlet, the traceless symmetric, and antisymmetric. There are all these 3 kind of operators for the ON models, and for each of them you get an ON vector. They have 3 components, and you can write the 3 system of equations in a compact way as follows. That you have a sum, which the sum runs over the representations are. The representations are S for singlet, T for traceless symmetric, A for antisymmetric, and well, there is a sum over delta, and then you have the OP coefficients and the ON vectors F, which has the index R and delta. So I hope this is clear. That so please remember that when I say R, I mean the R can take the values S, T, and A, and for ON vectors I have to work with these curly Fs, which have like 3 components.
Apratim, Wouldn't they? Why aren't they individually going to 0? I mean, these are different reps, right?
Right. No, the thing is, well, in the first, so so let me let me go back to where I introduced them. Here. Yeah, so in the S channel, they were different reps. If the bootstrap equation involved only the S channel,
I see. Okay, okay,
yeah.
all right. Yeah, okay, yeah, okay, great.
Makes sense.
Yeah, right. Yeah.
All right. So the when functionals for when, if given the form that I just showed, must have the following form that I'm showing now. So you can the first two components need to be omega minus because they must act on f minus, and the third guy must act on f plus. So it has to be a plus type function, right? Because any f is basically f minus, f plus, like this. So the when functionals must have this generic form, and we should also have the property that, well, this vector functional when it acts on the when bootstrap equation, it just gives you a sum over sum like the sum as follows. It just gives you a sum over r and delta, and then a sum over the when the vector functionals and the action of the vector functionals. So the action of the vector functional, the action of the vector functional omega is, I denote them as follows. So it as omega r comma delta, because omega can act on f r comma delta, curly f r comma delta. So that it has to carry an index level r and also the level of dimension delta. And so this is how it's defined. So please remember that when we have omega as a function of r and delta, so this is what it means. So now I present to you the first type of ON functionals, which I called simple functionals for ON. So the simple functionals for ON, they are simple because they can be derived right from the O1 functionals I have defined in the introduction. That's why they're simple. So, and it's consider the following form. Consider the following form that omega tilde, a certain kind of vector functional, is given as follows: that the first component is omega minus the alpha minus and beta minus guys, which I showed you before, the analytic functionals, and the third guy is a plus type analytic functional. So minus type, plus type, and with certain respective coefficients, A, B, and C. So if you have them, you already know the components. You just have to fix these coefficients. Just fix these coefficients. Fix these guys. So how do you want to fix them? Let's see how you want to fix them. But before that, let me tell you that since you already know the plus type, already know the analytic functionals, the components, you can already say that the action of this functional is finite, that they already satisfy finiteness, and they already satisfy the swapping property that I mentioned before. So the basic requirements are already satisfied. We just have to get have some more conditions, and let's see what they are. So it is possible to choose these guys. It is possible to choose these A, B, and C, so that if we have a functional like omega S, its action on the T-type vector for on the GFF guys, on the generalized free field values is 0. So this is, you can choose A, B, and C in such a way. So suppose you have a functional labeled, so you can create a functional labeled R, and if it acts on one vector with R prime, which is different from R, so this, if two tensor representations are different, then you get a 0. But this has to be it has to be evaluated at the GFF values also. This is a property that you can ask for. So it means the following orthogonality properties can be shown, can be derived. It says that if you have, by the way, the simple functionals are, I denote them as alpha tilde and beta tilde, and you can have the property that it's alpha tilde R, its action on R prime at double trace guys, they're given by the delta functions, and otherwise the derivatives are 0, and similarly for beta. Very similar to the O1 analytic functionals. And yeah, so so you can see these examples. These are all true. That alpha tilde A is acting on the singlet sector is 1, on the other sectors is 0, and so on. So this slide is to show an explicit example that you can choose alpha tilde in a certain way. So alpha tilde is chosen, if you choose them in this way, what do you get? So let's try to do it right now. We can just do it right now. So you have alpha n minus acting on f minus of f delta m, plus you have half of alpha n minus acting on f delta m minus, and we have minus half of alpha n plus acting on f delta m plus. And if you have delta m equal to delta n, then this guy is 1, this guy is 1, this guy is 1 also. So you get 1 minus half equal to 0. So it's a simple demonstration that you can have orthogonality properties in this way. So any questions so far? All right. So simple functionals have the following advantages and disadvantages. So some advantages of simple functional is that it's easy to prove the completeness relation. So by completeness relation, I mean that they have, so if a system of equation is complete, it means that it has the same info as the full Bootstrap equations. So solving the Bootstrap, all the information that you have in the full Bootstrap equation, they are all there in the simple set of simple functional equations. And the second advantage is that they're already quite useful because they have nice positivity properties. So this is the second, this is also quite important. So they're already good functionals to work with and get nice numerical results. So one disadvantage of this is, by the way, that they are not dual to the ON generalized free fields. So the ON generalized free, so maybe I was didn't show it properly. So I did show these orthogonality properties, but they are not exactly GFF. They are not exactly GFF because for ON GFF you must have double trace operators like this in the singlet and traceless channel, and odd double trace operators in the antisymmetric channel. But what these simple functionals do is that they are orthogonal in they're orthogonal for all traces, symmetric, antisymmetric, and singlet, all in the even double trace operators, which is not ON GFF. So this is one little problem that we have, but nevertheless, we can still use them. They're still good functions. So let me show you how they can be useful. And in order to show this, I have to talk a little bit about the O1 functional, some bounds that can be obtained from the O1 functionals. Just like one slide. So this is how a bound can be obtained from O1 functional. So one takes a combination as follows. One takes a combination of alpha minus and beta minus such that their action is the following. If you plot them against delta, their action is the following, where close to the identity, there is a finite value, some finite value. And but if you don't have identity, if you a little bit away from the identity, it's already, the action is too small. It's too small and also negative. This is important. So a little bit in this region at and a bit away from the identity is all negative, but it's also negligible. And after that, it's always positive. So this whole region is positive, and this allows you to put a certain bound on this region, which is a bit wider. So at when delta is at delta n, so you get a region where you don't have a double zero, and any OP coefficient that sits in this region has to have this upper bound. It's obvious because well, it cannot. So since you have a negative region, the OP coefficients cannot be too high, because otherwise the bootstrap would never be solved. So it should have an upper bound, and this is it. So these guys are known. So these q's are some known function. I haven't written explicitly, but so using this thing, you can set an upper bound to the OP coefficients, and it takes a simple form only when so it takes a simple form if it's also set n going to infinity. So the n going to infinity limit is just useful because it simplifies the expression for the bound. But so you already get this nice bounds for the OP coefficients, and so and the idea is that we can do the same thing with the ON simple functionals.
Apratim?
Yes.
So this delta n is some particular n, or some
this right? So this delta n here is not particular n. So it's like well, if you so when you choose these two functionals, alpha n and beta n, they carry an index, right? N.
Right. Yeah.
And so you can do this for any n. But and but when you set n to be very large, this whole plot simplifies.
I see. Okay. Okay. All right. Yeah.
Okay. So the idea is to make this work for the ON case. For the ON case, it's very easy to do this because, well, this whole bound was obtained with minus type functionals, and to make it work, we choose a combination of ON functionals which are also simply proportional to omega minus. So to do this, we take a combination as follows: omega s, omega t, and omega a, whose components are only omega minus, and the third guy, which was omega plus, is just set to 0. This is what you require, and this is possible by choosing either a certain combination of omega s and omega t. It just comes from their respective forms. There is no, I can't say anything more about this. And also it can take a certain combination of omega s and omega a, both of which gives to this form. And these two properties also have this nice property that their actions on the respective channels are always positive. This is also important. So you have the proportional to omega minus, and their action already looks like the following, looks like these plots. And once you have this, you can build similar upper bound functionals. So it's the same story. It's basically you just have obtained functionals which are vector functionals whose components are the minus type guys, and you can combine them to get these upper bound functionals, just like the one case, and it gives you upper bounds on OP coefficients of the respective singlet chrysosymmetric and antisymmetric sectors.
Apratim?
Yes.
So just a heads up. So it's been an hour into the seminar. So we
yeah.
usually go up to 4:30. So you have like, you can go for another 20 minutes.
Right. Okay. So right. Actually, I didn't intend to finish this whole talk. I just had in mind that I should go as far as possible, but I think I already am like 87 to 80% into my talk. So
okay, great. Yeah.
Okay. I can finish it.
Okay.
So and similarly, you can also have a lower bound. So the lower bound for the O1 case is this is the O1 lower bound for the O1 case, and here we choose a functional which has the property like it's positive near the identity. It's also positive in most other places except close to delta n. When it's close to delta n, it's negative. So this is the property that you have. So only at a region nearby delta n, it is negative, and every other place is positive. So here it says this functional means that any OP coefficient in this region cannot be lower than a certain value. So it gives a lower bound. So this is what allows you to get a lower bound on O1, and just like what I showed above, you can combine the O1 simple functionals in the following way, and it allows you to get lower bounds on OP coefficients of OP coefficients in the respective sectors. So yeah, so you see that just by looking hard at the O1 functionals, I'm getting bounds on the ON coefficients. Okay, so this is the end of the simple functional story. So I will pause here and ask that too, if anybody has any question. No? All right. So now let me move on to the second type of functionals, which is given by which I'll call the GFF functionals. But before that, let me tell you a little bit about the ON generalized free fields. The ON generalized free fields are basically given by the following. So you can see that this is an ON correlator with I, J, K, L indices, and it's crossing symmetric, and it can be decomposed as follows, as conformal blocks in the singlet chrysosymmetric and antisymmetric sectors, and then you get that the singlet and chrysosymmetric has even double trace guys, and the antisymmetric sector has odd double trace guys. So this is ON GFF in short. Yeah, so looking at the ON GFF, I demand that there should be I now require functionals which also must satisfy a basis, just like the O1 case. So in one case, I showed that any F minus can be expanded in the basis of F minuses of double trace operators. Here I demand that this ON vectors, the full ON vector allows an expansion of in terms of ON vectors evaluated at these guys. So it should be +1. So evaluated at this position. So when vectors of singlet one vector at delta n, fresh symmetry one vector at delta n, and antisymmetric one vector at delta n +1. So, and their respective derivatives. So is this possible? So yeah, this is indeed possible, but and proof is very similar to the O1 story, but let me just assume that this is true, and let me find out whether it is possible to derive these coefficients. So I will try to construct some functionals which give me these coefficients. If that is possible, I have what I need, and it's almost a proof to the existence of this basis. So yeah, so the GFF functionals are what I need for this to get the coefficients of this basis expansion, and the GFF functionals have the following form. So each component of a GFF functional is basically like the following. So I write down an ansatz for this, and it's an integral, and I already showed you a singular integral for the one, and this integral. So these are certain integrals with certain functional kernels, which are dependent on I. So the I is the level of the component, and I must choose these kernels in a certain way. So first of all, by the way, so the action of this whole vector is defined as follows. So it's basically an integral like the following. It's basically an integral over dz and giz, and a sum. So a sum over gi and well, an ri is a component of these guys. So it's an integral, so like the following, and similarly as an integral of sum over fi and ri and the real part of g delta z. So this form basically comes from this definition by a contour deformation. So this is the action of the vector functional now, and I'm skipping the details, but you can choose them. So, and now I require them to have these properties of picking out these OP these basis coefficients, and this can be done by demanding these equations. So I have so if I demand that this equation be true, so this whole equation comes from the fact that you have to combine this guy, and you have to choose these into a certain combination. Choose these integrants in a certain combination such that you get what you need. So, and this gives you what I call a fundamental free equation. So requiring the kernels to satisfy these properties will allow you to choose, will allow you to solve for the GFF functionals. So, and further you have to, they must satisfy some conditions of these conditions, like a certain certain fall off as z goes to infinity, at z goes to infinity. So it must fall off as z to the -2, which is for finiteness. And also you have to satisfy orthogonality properties, like before. And yeah, so, and this allows, and this basically gives you what you need. I don't show the exact form of the GFF functionals, but well, they have they have these orthogonality properties, and they also and these are the and then if you use them on the Bootstrap equations, you get a set of 6 equations, functional Bootstrap equations, because there are 6 of these GFF functionals. So you get a system of 6 equations by acting them on the Bootstrap, by the 3 Bootstrap equations. Yeah. So okay, so I think I had a slide for the connection with Polyakov Bootstrap, which I think I'm going to skip because it's been already too long. So I will just show you. So I'll just show you one advantage of the GFF equations it's that it can be shown that the action of the GFF functionals, they can directly derive from the Witten diagram coefficients, from Witten diagrams. So this is one real advantage of working with GFF functions. So and Witten diagrams are quite well studied, and these expressions are quite simple, and functionals, they are integrals, so their action is quite hard to evaluate. So if there's a shortcut to compute them, it's really nice, and Witten diagrams give you that. So this is one important thing that I wanted to say. And then finally, these are like my last 2 slides. I wanted to say that how do you obtain a general global symmetry, because I promised you that it's a general global symmetry. I can obtain general global symmetry functionals, and I just showed you the ON. So let me show you a little bit of how it can be generalized further. So for general global symmetry, what you do is you basically expand the full correlator into blocks with the tensor structures for the group you have. You identify the tensor structures, and then you find out a certain crossing relation. So it's a crossing relation for the T's, for the tensor representations, and it is expressed in terms of a matrix called the crossing matrix. And the whole Bootstrap equation can be now expressed in the following way. So this is how the generic Bootstrap equation can be written, where this curly f r prime is nothing but is basically written in the following way. So it's a certain matrix times f minuses and another matrix with f pluses, and these matrices are directly dependent on the crossing matrix C. So this is how the whole general group crossing story can be expressed, and its relation to what I said before is just a change of basis. So this whole thing is just a change of basis. So previously I was working the basis of eigenvectors of this matrix C, and now I'm working in within the vectors of this C matrix. And to get the general global symmetries, so this is the flowchart that if you have, for example, the ON functionals, you can use this change of basis to obtain functionals for that act on these guys, F R R prime. And then you identify then you try to identify the dependence of the crossing matrix, the ON crossing matrix, and then just generalize it to the usual, the general crossing matrix that you have, the general group, and then that automatically gives you the general functionals for the group you want. So you just have to identify how the dependence on the crossing matrix. So yeah, so this is very simple. That's why I wanted to point out, and this is like the end of my talk. So let me summarize. So I showed you that analytic. So you can construct a set of functionals called analytic functionals, which are dual to GFF, which means that it trivializes the generalized free field CFT, and it's a very powerful non-perturbative tool for solving CFTs, but also while you have an analytic understanding of the picture. For global symmetries, you can have two types of functionals. One I call the simple functionals, which are simply the combination of one functionals. And then you can also have the GFF functionals, which are basically will optimize or trivialize the ON GFF CFT. And third, well, interesting bounds can be obtained. They're already obtained from the simple functionals. I didn't show you applications of GFF functionals because that needs some of the talks, but some nice bounds can already be obtained from simple guys. And finally, the GFF functionals are connected to the Polyakov Bootstrap, the Polyakov Bootstrap story, and just like the O1 GFF functionals are often connected to the Polyakov Bootstrap for O1, and hence the functional actions can be directly obtained from written diagrams. And so it's a nice shortcut to have. Oh, all right, so this is the end of my talk.
Okay, so let's thank Apratim for the great talk. Okay, if there are any questions, you can go ahead.
So Shubham is here. He's late.
Hello.
Hello.
Hello. What's up?
You're late.
Yeah, I was 20-30 minutes late actually, but yeah, I think I got most of the stuff. Right.
So Apratim, I have like a vague question, like
Yes.
a general question. So in the Bootstrap picture, so we usually consider the 4-point functions, right?
Yeah.
But you know, in CFT, there are also these pentagon relations and hexagon relations and so on for higher point functions. So what happens if you consider them? I mean,
well, so basically you are asking about Bootstrap for higher point functions.
Yeah, right.
Okay, so my knowledge is a bit limited, but I can tell you that, well, not many work has been done for Bootstrap higher point functions, but I think there are some papers which, so by the way, for higher point function, it's, okay, by the way, I should get rid of, I wanted to tell you something about applications, but well, time didn't permit. So for higher point functions, you can have the following kind of channels. You can have something like a something called the Coombe channel,
okay,
which looks like the following, called the Coombe channel.
Right. Okay.
And you can also have something, well, for at least for, you can also have other kinds of channels. And for example, there can be something called the snowflake channel for 6-point functions.
Right. Yeah.
And I think there are papers that discusses crossing equation for these for one Chrome channel and one snowflake channel. I'm not sure, but there is one paper by Pedro Vieira that
I see.
that has this.
Okay, all right. Okay, yeah. Thanks. Because like in this RCFT papers by Moore and Seiberg, like long ago, so they discuss these Pentagon identities, which is roughly like this: like take something in the COM channel and then do a set of mutations, S channel to T channel in the subgraphs, and then you come back to itself. But I have never seen it used in the Bootstrap programs. I was just wondering. Okay.
Yeah, I think it's not so advanced.
Okay.
Yeah, and also I think like first of all, it's hard to get the blocks. Like we don't know blocks in all of the channels for higher point functions. And from a Bootstrap perspective, you can see that the graphs that Apratim has drawn, those are basically the 4 points. Like you are combining 4 points. You can reduce it to, you can sort of see that you can think of it as a 4-point, and then there is a 3-point attached to it.
I see.
So in some sense, if you can solve the 4-point function, then 5-point function will not give you any extra more constraining or something. Like it will give you at most whatever you are getting from the 4-point function.
I see. Is that known that you wanted any new information?
Yeah, I mean, so there is a theorem that tells you that if you can solve all the 4-point function of a CF, then you don't need to
I see.
for the high point functions. But that you should see as, I mean, of course, I mean, right now we can't solve all the 4-point functions. So we need something new. So that is true. But in principle, we own. That's what
I see. Okay. Great. Okay. Thanks. Okay. So I'll stop recording then.
Sure.